Hi everyone. We're going back to the equation we solved last time. 2 sine of 4x equals negative root 3. Before, we solved it over all real numbers, and we got all real solutions. It was represented by this general solution set over here. The set of all x in the reals, such that x was a member of this first group, I'll call group 1, or x is a member of this second group, which I'll call group 2, where n is an integer. You should write that. Okay, now believe it or not, the harder problem is finding solutions specifically in this interval. In part because I advise that you find the general solution first anyway. So whether I ask you to find all real solutions or the solutions only in this interval or some other interval, I advise you find the general solution set first anyway. And then there's more work to get what these particular angles, solutions are going to be in that interval. And it turns out we have many particular solutions in this interval. All right, let's go through these two groups. Now, one way you can do this is by plugging in various integer values for n, but we can make things a bit more efficient and systematic. All right. We're going to use the idea of incrementing, and it comes from basically the distributive property. So here's the idea. If we start with n equals 0, and we will, then we cover this term up and we're left with pi over 3. So pi over 3 will be a particular solution in this interval. But then we're going to let n equal 1, 2, and so forth. We'll see how far we have to go before we hit 2 pi or beyond. But instead of plugging in n equals 1, n equals 2, and so forth, which you could do, here's the idea. Let's say that we increase the value of n by 1. So we go from n to the quantity n plus 1. We go from n to the quantity n plus 1. Now, if we substitute n plus 1 for n over here, what happens? The pi over 2 can distribute through this, and we get pi over 2n plus pi over 2. So again, I'll write that out. If you replace n plus 1 into the n here, if you have pi over 2, all times not n, but the quantity n plus 1, when you distribute, what do you get? You get pi over 2 n, like what we have here, but you get another piece, plus pi over 2 times 1, plus pi over 2, which is an additional piece. So what's the point I'm making here? Every time you increase the value of n by 1, that's like an incrementing. Every time you increase the value of n by 1, for example, let's say you go to the next integer, from 0 to 1, from 1 to 2, and so forth. Then basically, you're adding pi over 2 to this right-hand side. You're adding the coefficient pi over 2 here to the right-hand side. Same for over here. So let's apply this principle. We're going to start with pi over 3, and we're going to keep adding pi over 2 until we get into trouble here. All right. Group 1. Remember, group 1 consisted of these solutions. These were all the real solutions that corresponded to what came from this point over here. And then remember, we had to divide by 4. We'll talk about that. We basically take this and divide by 4. All right, group 1. We could plug in n equals 0, 1, and so forth, but let's do it faster. All right. Now, when n equals 0, this term dies out, and we're just left with pi over 3. And pi over 3 is in the interval we want, from 0 to 2 pi. And then we're going to increment. We're going to keep adding, or if necessary, subtract, by pi over 2. We're going to start with pi over 3, and we're going to keep adding, and if necessary, subtract by pi over 2 to get more solutions in this interval. But the problem is that we need a common denominator. And right off the bat, you see why this problem is already harder than the previous problem. where I wanted all real solutions, because we're dealing with all these fractions and denominators and all this. And we have to add these unlike fractions, which we didn't really have to do before. All right, let's get these in terms of 6, because 6 is the LCD if we're dealing with thirds and halves. All right, so how do we get from pi over 3 to 6? Well, 3 times what is 6? 3 times 2 is 6, so we multiply the top by 2. Pi times 2 is 2 pi. Pi over 3 times 2 over 2 is 2 pi over 6. That's how we build up that fraction. For pi over 2, we're multiplying by basically 3 over 3, which is a form for 1. We're multiplying by 1, really. Pi over 2 times 3 over 3, we get 3 pi over 6. Pi over 2 times the 3 pi over 3 gets us 3 pi over 6. All right. So how are we going to do this? And again, you could just plug in values for n, but let's do this. We're going to start with pi over 3, which is simplified. And in fact, I'll box it in red. That is going to be one of our final solutions in the solution set. All right. Now, the thing is, we're going to keep adding pi over 2. So for now, it's easier for us to reinterpret pi over 3 as 2 pi over 6. And we're going to keep adding. One reason why I call this the increment is that this is meant to have you recall Picapia from before. Remember in Picapia, the hardest part about a Picapia problem was finding the x or theta coordinates, right? I had to get from the phase shift, or 0 maybe, to here, and then to here, and then to here, and then to here. And we use the idea of an increment, a thing that we add to get to each new coordinate for these grid lines. Well, similarly, we're going to start with 2 pi over 6, and we're going to keep adding pi over 2 in the form of 3 pi over 6. So we're going to start with 2 pi over 6, and we're going to keep adding 3 pi over 6. All right. Now, before we even talk about adding, we can even ask ourselves, as a thought experiment, what's 2 pi over 6 minus 3 pi over 6? Do we get anything good? Well, 2 pi over 6 minus 3 pi over 6, that's negative pi over 6. That's no good. That's too low. That's outside of this interval. And in general, if back over here, if you pick the least non-negative representative for this point, in this case 4 pi over 3, then you shouldn't have to do any subtracting. Okay, but we're just playing it safe. All right, so don't subtract. We add 2 pi over 6 plus 3 pi over 6. So we go in the right direction. 2 pi over 6 plus 3 pi over 6 gets us another solution, 5 pi over 6. And notice this is simplified, so I'll box it in. In fact, on an exam, I might even accept it if students just box in all of their solutions. Though technically, remember that an answer to a solve an equation problem should really be a solution set. But in the meantime, let's box these in. Now, what's 5 pi over 6 plus 3 pi over 6? That's 8 pi over 6, but we need to simplify that. That simplifies to 4 pi over 3. All right. Now, for addition purposes, let's go back to 8 pi over 6. We're thinking in terms of sixths when we're adding the increment. What's 8 pi over 6? Again, plus 3 pi over, again, plus 3 pi over 6. 11 pi over 6, which is simplified. By the way, it so happens these are famous angles. Well, these don't have to be famous. It's possible that in other problems, you might get pi over 24 or something like that. So we're just kind of lucky that these happen to be special angles. Now notice 11 pi over 6, that's knocking on the door of 2 pi. 11 pi over 6 is just barely below 2 pi. So I think we're done. But just to be safe, let's think about it. What's 11 pi over 6 plus 3 pi over 6? That's going to be 14 pi over 6. Or 7 pi over 3. Nope, that's too big. 7 pi over 3 is bigger than 2 pi. That's not going to be a solution that we want now. So we cross that out. So these are the only 4 particular solutions we get from group 1 that are in this interval. from 0 to 2 pi. By the way, if we were to get 2 pi, we would eliminate it because of this parenthesis over here. 2 pi is coterminal with 0. So if 0 is a solution, we usually don't want 2 pi also. All right. Now you might be asking, the fact that we have 4 solutions in here, is that a coincidence? Well, not quite. Remember, in the original equation, we had 2 sine of 4x equals negative root 3. Or you can look at it this way. We're looking at this equivalent equation, sine of 4x equals negative root 3 over 2. In fact, I'd like to focus more on this equation. Now, the fact that we have 4 solutions in group 1, that's not a coincidence. The fact that there's a 4 there in front of the x, that does have an impact. So the fact that we have a 4x here, yes, that is related to the fact that we have 4 solutions from group 1. However, I don't want to make a blanket statement because if you're dealing with quadrantal angles, for example, or if you're using symmetry, then that might not be the case. So I don't want to say that just because 4 is in front of x, that's going to be the number of solutions you get in any given group, because it depends how you're using symmetry. It depends if you're dealing with quadrantal angles. So I'm not ready to set that in stone. I will just say for now, because we're dealing with sine of 4x, it is not a coincidence that we happen to have, well, it's not a coincidence that we have 4 solutions in group 1. By the way, we could have obtained these by plugging in n equals 0, 1, 2, and 3. But again, even though you might guess that these are the 4 appropriate values of n to plug in, it's not ironclad. So you should go through these one by one. But it is true that these 4 values of n will get us these 4 particular solutions in group 1 that we want. You could have guessed at that, but to be extra sure, we went through these one by one. Because remember, if you're using certain symmetries or if you're dealing with quadrantal angles, then it might not be 4 solutions. For example, you might be dealing with tangent or cotangent. That has a different period. All right. Anyway, we're not done yet. That was just group 1. What about group 2? Although in group 2, I have less blabbing to do, right? And it turns out we don't have to simplify much. Here, we're going to start with 5 pi over 12. Okay. The increment, again, is going to be pi over 2, the coefficient on n. But we want that in terms of twelfths. Pi over 2 times 6 over 6. Pi over 2 times 1 in the form of 6 over 6 gets us 6 pi over 12. So we're going to start with 5 pi over 12, and we're going to keep adding 6 pi over 12. Now, again, 5 pi over 6, I'm sorry, 5 pi over 3 was our smallest non-negative representative for this point over here. So it turns out we won't have to subtract. Actually, I'm now explaining why it is we picked 5 pi over 3 as our representative for this point, because many students may have picked negative pi over 3. In fact, if I had just wanted the general solution on R, negative pi over 3 might have given us a more efficient solution set. But if we eventually want to find solutions between 0 and 2 pi, it's actually better for us to take the least non-negative representative for this point. So the 5 pi over 3 turns out to be better than negative pi over 3 if we ultimately want to find solutions in this interval. Okay. So 5 pi over 3, that's our least non-negative solution, which means that when we deal with 5 pi over 12, we shouldn't have to subtract. And we don't have to. You can see here that 5 pi over 12 minus 6 pi over 12, that's no good. That's going to be negative pi over 12. That's outside the interval from 0 to 2 pi. I'm going to blue now. We still only want particular solutions between 0 and 2 pi. All right, well, here they are. And they're simplified as we go along. 5 pi over 12 plus 6 pi over 12 is 11 pi over 12, simplified. 11 pi over 12 plus 6 pi over 12 is 17 pi over 12, that's simplified. And 17 pi over 12 plus 23 pi over 12, simplified. We get our 4 solutions from group 4. This last one is very, very close to 2 pi. If you try to add again 6 pi over 12, you're going to go over. So once again, we only have 4 solutions in group 2. Again, it's not a coincidence that we had sine of 4x in our original equation. So it's no coincidence that we have 4 solutions in group 2, but still it's better to be sure. But if you had to guess, you might guess that you would need to plug in n equals 0, 1, 2, and 3, these 4 values for n. And if you make that guess, you'd be right. However, if you try to plug in directly, it might be harder for you to do it one by one. It might take more time. I think this incrementing technique is faster. Start with 5 power 12. You don't have to subtract. Keep adding. And then don't add from here. You're going to go over. So finally, we get 8 solutions when we gather together the 4 solutions from group 1 and the 4 solutions from group 2. Here, I did not sort them. I did not order them. If you want, you can put them in order. It would be power 3 first, and then 5 power 12, then 5 power 6, then 11 power 12. If you wish, you can sort these, but you don't have to. Sets are unordered, and I would accept the solution set. In fact, on an exam, I might have been happy if you just boxed these 8 values in. But remember, the answer to a solve an equation problem is technically a solution set. If you want to sort or order these, great, but you don't even have to do that. And these are all the real values of x in the interval from 0 to 2 pi that will solve this equation up here. In the next video, I'm going to discuss Desmos, and I'm going to discuss the relationship between theta and x in the next video.